Microsoft just told the world it can build a working quantum computer 3 years faster than it promised before. There is just one problem. The company has not proven that the particle its entire machine depends on actually exists. Read that again slowly, because this is not a story about a delay. It is a story about a company racing toward a finish line while the track underneath it may not be real. In June 2026, at its Build Developer Conference in San Francisco, Microsoft unveiled a new quantum chip called Majorana 2. The announcement was simple on the surface. The company said it had cut its quantum computing timeline in half, moving its target for a scalable, commercially useful quantum computer from the mid-2030s to 2029. Like and subscribe, because what happens next will change how you think about every breakthrough headline you have ever scrolled past. To understand why this claim is so explosive, you need to understand what Microsoft is actually trying to build. Most companies racing toward quantum computing, including Google and IBM, use qubits made from superconducting loops or traptons. These qubits are fragile. They lose their quantum state in microseconds, and engineers have to bury them under mountains of error correction just to get useful results. Microsoft chose a different, far riskier path almost 2 decades ago. It bet everything on something called a topological qubit, built from a theoretical particle named after Italian physicist Ettore Majorana. A Majorana zero mode is not a normal particle. It is a strange, ghost-like state that can appear at the ends of a superconducting nanowire when conditions are exactly right. In theory, pairs of these states can store information in a way that is naturally protected from noise and interference. Now understand what that means. If Microsoft is right, its qubits would not need the same brute force error correction every competitor depends on. The information would be locked away by the geometry of physics itself, not by a software patch layered on top of a fragile system. That sounds like magic, and for over a decade it has acted like a phantom too. In 2018, a team connected to Microsoft published a paper in the journal Nature claiming it had detected a Majorana zero mode in the lab for the first time. It was treated as a milestone. Scientists across the world cited it, built on it, taught it to students. But that's not even the worst part. In 2021, the paper was retracted after outside physicists discovered that the original data analysis did not meet basic scientific standards. The signal that was celebrated as proof of a new particle had not actually been proof of anything at all. Like and subscribe, because most companies would have walked away from a public retraction like that. Microsoft did not. It kept funding the program for years quietly, while skepticism in the physics community grew louder. Then in February 2025, Microsoft returned with a chip called Majorana 1, claiming it had finally built a working topological qubit. The announcement triggered a fresh wave of controversy. A Nature editorial team, reviewing the accompanying paper, stated plainly that the results in the manuscript did not represent evidence for the presence of Majorana zero modes in the devices being described. Read that again slowly. The very journal publishing Microsoft's research said the paper did not prove the thing the press release claimed it proved. Now, in June 2026, Microsoft has doubled down again. With Majorana 2, the new chip swaps the aluminum used in earlier devices for lead as the superconducting material, paired with an updated semiconductor layer combining indium arsenide and indium arsenide antimonide. According to Microsoft, this change produces a topological energy gap more than twice as large as before, which is supposed to shield the fragile quantum state from outside noise. The company reported that its qubits are now over 1,000 times more reliable than the previous generation, with a measured parity lifetime of roughly 20 seconds compared to under 12 milliseconds in earlier chips. That is not a small improvement. That is the difference between a flashlight that flickers for a fraction of a second and one that stays steady for nearly half a minute. But that's not even the worst part of this story, and here is where it gets disturbing. Demonstrating a true qubit requires two distinct types of measurement, known to physicists as X and Z measurements. Together, they confirm that information is being stored and manipulated the way a real qubit should behave. Microsoft's new paper on Majorana 2 presents only the Z measurements. The X measurements, the second half of the proof, are missing entirely. The company's own researchers acknowledge in the paper that investigating this gap will be, in their words, an important direction for future work. Now let that land, the chip Microsoft is using to justify cutting its roadmap in half has not yet cleared the basic bar required to call it a functioning qubit. Physicists outside the company have not been quiet about this. Henry Legg, a physicist at the University of St. Andrews in Scotland, stated bluntly that nothing in the new preprint resolves the fundamental issues that have plagued Microsoft's claims for years. Vincent Murick, an experimental physicist in Germany, went further, describing the announcement as just another step in what he called Microsoft's almost decade-long track record of publishing unreliable results. These are not random critics on social media. These are condensed matter physicists who study exactly this kind of device for a living, and they are telling the public in plain language that the Emperor's new chip may have no clothes. Now understand what that history of conflicting verdicts actually teaches you as a viewer, far away from any physics lab. When experts who have spent entire careers studying the exact same data cannot agree on what it proves, the honest answer is not that one side is lying. The honest answer is that the science genuinely is not settled. Yet, no matter how confident either side sounds on camera, like and subscribe, because the gap between what a press release says and what a peer-reviewed paper proves is exactly where modern tech hype lives and breathes. Microsoft framed the 20-second parity lifetime as proof that its qubits are stable enough to build toward a real machine. Legg disagreed directly with that framing, arguing that a long parity lifetime is not the same thing as proving the device behaves as a genuine, controllable qubit. Chetan Nayak, the Microsoft physicist leading the project, pushed back just as directly, stating that parity lifetimes translate straight into qubit lifetimes. Two trained physicists, looking at the same 20 seconds of data, reached completely opposite conclusions about what it actually means. Now here is where the story gets bigger than one chip. Microsoft is not just claiming a materials science improvement. It is using that improvement to justify having its entire commercial roadmap, publicly stating it now expects a scalable, practical quantum computer by 2029 instead of the early 2030s it had cited before. Chetan Nayak wrote that the rapid recent progress, partly enabled by Microsoft's own agentic AI research platform called Discovery, gave the team confidence to accelerate. Discovery is designed to run autonomous AI agents that assist scientists with experiments, material design, and data analysis. In other words, Microsoft is using artificial intelligence to help build the very hardware that AI itself may eventually run on. That loop should make you pause, like and subscribe, because this is the part almost nobody talks about. If Microsoft's roadmap holds, even with all the unresolved scientific questions, the implications stretch far beyond Microsoft's balance sheet. Quantum computers at true commercial scale are not just faster calculators, they are existential threats to the encryption, protecting your bank account, your government's classified files, and the private messages you sent 5 minutes ago. Researchers have estimated that breaking our SA-2048, one of the encryption standards securing much of the internet, could require somewhere between roughly 1 million and 20 million stable, error-corrected qubits, depending on which algorithmic assumptions you use. Microsoft's Majorana 2 chip currently has 12 qubits, not 12 million, 12. That gap is enormous, and it matters because it tells you something the headlines conveniently leave out. Even if every unresolved physics question about Majorana particles gets settled tomorrow, scaling from a 12-qubit lab device to a million-qubit cryptography breaking machine is not a matter of adding more chips to a server rack. It requires manufacturing precision, error correction architecture, and control electronics that nobody on Earth has ever built at that scale for any qubit. Technology, topological or otherwise, now understand what that really means. The 2029 date is not a prediction about engineering. It is a bet on physics that has not yet been proven, layered on top of an engineering challenge that has never been solved by anyone, for any company, using any approach. Read that again slowly, because here is the irony sitting underneath this entire announcement. Microsoft's argument for why people should trust the 2029 timeline is the same argument the company has made twice before, in 2018 and again in 2025, both times followed by public retraction or unresolved controversy. The pattern is consistent. A press release lands first. Bold language follows, words like breakthrough and milestone. Then, weeks or months later, physicists outside the company comb through the data and find the proof falls short of the claim. Each time, Microsoft adjusts its language slightly, narrows its specific assertion, and announces the next chip as the one that finally settles the debate. Majorana 2 is being sold the same way. Like and subscribe, because not every skeptic is dismissing Microsoft entirely, and that nuance matters too. Physicist Kartik Agarwal at Argonne National Laboratory called the new measurement method genuinely positive progress, saying it supports the case that the devices are showing real, non-local Majorana behavior. Materials scientist Iver Martin, also at Argonne, described the underlying device as a remarkable achievement from a fabrication and materials standpoint, separate from the question of whether it proves topological qubits exist. So this is not a simple story of liars versus truth-tellers. It is a story of genuinely difficult physics, where even experts examining the exact same 20 seconds of data land in different places. But that's not even the worst part of where this leaves the rest of the industry, while Microsoft pours resources into a technology still fighting for basic scientific acceptance. Competitors using superconducting and trapped I-don't qubits are scaling steadily, with less theoretical risk and a clearer, peer-reviewed path forward. If Microsoft's bet pays off, the company leapfrogs an entire industry overnight, because topological qubits, if real, would need dramatically less error correction than every rival architecture. If the bet fails, Microsoft will have spent 2 decades and untold billions of dollars chasing a particle that may simply behave differently in theory than it does in a real laboratory device. Now let that sink in. This is not a small research side project buried in a university lab. This is one of the most valuable companies on the planet, with a market capitalization in the hundreds of billions of dollars, publicly tying its long-term computing strategy to a particle that respected physicists are still arguing does not have confirmed proof of existing inside Microsoft's own hardware. The stakes are not abstract. Microsoft stock, its enterprise cloud contracts, its government partnerships, and its entire AI infrastructure narrative are all quietly resting on the assumption that Majorana zero modes behave exactly the way Microsoft's internal theorists predict. Like and subscribe, because here is the historical context almost every viral headline skipped entirely. Winfried Hensinger, a physicist at the University of Sussex who works on a competing trapped I-don't approach, said publicly that topological quantum computing as a field is probably 20–30 years behind other quantum platforms already in development. Even if Microsoft's underlying physics turns out to be correct, the company may simply be too far behind time-wise for a 2029 commercial machine to be realistic at any meaningful scale. A peer-reviewed publication confirming Majorana zero modes is one milestone. A working logical qubit built from them is another. A million-qubit, fault-tolerant, commercially useful quantum computer is an entirely different mountain, sitting several mountain ranges further down the road. Read that again slowly, because the timeline compression Microsoft is advertising assumes that every one of those mountains gets crossed in roughly 3 years, starting from a chip that has not yet passed the basic X measurement test required to confirm it is a real qubit at all. That is the gap between the press release headline and the laboratory reality. Microsoft is not claiming to have built a quantum computer. It is claiming to have built a component that might eventually, after years of additional unproven engineering, become part of one. The distance between those two claims is where almost all of the genuine uncertainty in this story actually lives. Now here is the part that should genuinely unsettle you, Microsoft has financial incentives, competitive incentives, and now public credibility on the line to keep insisting. Its timeline is real. Every quarterly earnings call, every AI infrastructure pitch to enterprise clients, every conversation with government partners about national security and post-quantum cryptography benefits from Microsoft appearing to lead the quantum race. That pressure does not make the company dishonest, but that's not even the worst part. It does mean the incentive to announce progress, loudly and often, will always be stronger than the incentive to wait quietly until independent physicists fully agree the underlying science is settled. Like and subscribe, because this dynamic is not unique to Microsoft, and that is exactly why this story matters beyond one chip. The entire technology industry has learned, especially since the AI boom accelerated, that bold timelines generate headlines, headlines generate investor confidence, and investor confidence generates capital. For the next round of research, whether that capital eventually produces a working quantum computer or simply funds another decade of incremental, contested progress, is a question nobody, including Microsoft's own physicists, can currently answer with certainty. Now understand the human stakes hiding underneath all of this corporate science. If a true, scalable quantum computer arrives by 2029, the encryption protecting global banking, military communications, and personal data overnight becomes vulnerable to a category of attack that did not meaningfully exist before. Governments around the world are already racing to deploy post-quantum cryptography standards, specifically because nobody wants to be caught unprepared if any company, Microsoft or otherwise, actually crosses that threshold first. The urgency around that migration does not depend on whether Majorana 2 is real. It depends on the fact that someone eventually probably will get there, and nobody knows exactly when. Read that. Again slowly, because that uncertainty is the real headline, far more than the specific number 2029. Microsoft is not promising magic. It is promising acceleration on a path that still has unresolved scientific gaps, unproven manufacturing steps, and a documented history of overstated announcements followed by quiet corrections. The 12 qubits on Majorana 2 are real, measurable, physical objects sitting in a lab in Washington state. Whether they are topological qubits in the way Microsoft's marketing department describes them is, as of today, still an open scientific argument, not a settled fact. Like and subscribe, because here is the closing twist that brings this entire story back to where it started. Microsoft told the world it had cut its quantum timeline in half. What it did not say in the headline of the announcement was that the chip behind that claim has not yet passed the test required to prove it is a real qubit. At all, the press release spoke with total confidence. The physics, examined sentence by the people qualified to judge it, spoke with considerably more doubt. Somewhere between those two voices sits the actual truth about how close or how far we really are from a working quantum computer. Now let that land, because the lesson here is bigger than quantum physics. Every time a company tells you it has halved a timeline, ask, what evidence supports the half it kept quiet about? Microsoft's 20-second parity lifetime is a genuine technical milestone, worth taking seriously. But a press release confidently declaring a 2029 commercial quantum computer, built on a chip still missing half of the measurements needed to call it a true qubit, is not a finished discovery. It is a bet dressed up as a breakthrough placed in front of an audience that mostly will not read past the headline. To really understand how unusual Microsoft's bet is, you have to look at what everyone else in this race is doing instead. Google's quantum team has spent years scaling superconducting qubits inside a chip called Willow, focusing almost entirely on proving that error correction improves as the chip gets bigger. That is a slow, grinding, mathematically provable strategy. Add more qubits, measure the error rate, prove it drops, repeat. IBM has taken a similar superconducting path, publishing detailed, peer-reviewed roadmaps with named hardware milestones stretching out for years. Neither company is promising a magic shortcut. Both are betting on brute force engineering over exotic, unproven physics. like and subscribe, because that contrast is exactly why Microsoft's announcement stood out so sharply inside the physics community the moment it dropped. Trapped I-don't companies, like the one Winfried Hensinger works with, take a third approach entirely, using individual charged atoms suspended in electromagnetic fields as their qubits. This method is slower to scale but extremely well understood, with decades of peer-reviewed precedent behind every claim made about it. None of these competitors are racing toward a 2029 deadline. Most major superconducting and trapped I-don't roadmaps still target the early to mid-2030s for similar commercial milestones, and they do so while publishing complete, independently reproducible data. At every stage, now understand why that matters. Microsoft is not just claiming to be faster. It is claiming to be faster using a method that strips out the very error correction overhead its competitors depend on, based on physics that a meaningful slice of the field still considers unconfirmed. Read that again slowly, because the history here goes back further than most viewers realize. Microsoft began seriously pursuing topological quantum computing around 2006, nearly 2 decades before Majorana 2 ever existed. For most of that time, the company published almost nothing publicly, running quiet academic partnerships with university labs in the Netherlands, Denmark, and the United States. The strategy was patient by design. Topological qubits, if they worked, promised a structural advantage no other architecture could match, so Microsoft was willing to wait far longer than its rivals for a payoff that might never arrive. That patience is part of why the 2018 Nature retraction stung so badly inside the company. Years of quiet, expensive research had produced a headline result that, under closer inspection, did not hold up. Like and subscribe, because what happened after that retraction tells you everything about how seriously Microsoft was willing to gamble on this one idea. Instead of pivoting toward superconducting qubits like its competitors, Microsoft rebuilt its experimental protocols from scratch, brought in new device fabrication techniques, and spent years developing what it called a topological gap protocol, a measurement standard meant to filter out false signals before publishing any future claims. That protocol became the backbone of the Majorana 1 announcement in February 2025, and almost immediately, outside physicists began attacking the protocol itself, arguing it was built in a way that could let non-topological signals pass the exact same tests a real topological qubit would pass. Now let that land. The very tool Microsoft built to avoid repeating its 2018 mistake became, in the eyes of critics, a new version of the same mistake, dressed up in more sophisticated language. That criticism set the stage for the tense atmosphere surrounding Majorana 1E's debut at the American Physical Society's Global Physics Summit in March 2025. Chetan Nayak presented Microsoft's data to a packed room, promising solid evidence after months of public pressure. But that's not even the worst part of that meeting. Physicist Henry Legg gave a separate talk the day before, in a much smaller room, laying out fundamental doubts about Microsoft's entire measurement approach before Nayak ever took the stage. Scientists who attended both talks described the contrast as stark: one, a headline event filled with confident language; the other, a quieter, technical dismantling of the assumptions underneath it. Microsoft's data, according to several physicists present, was impressive from a materials engineering standpoint, but underwhelming as proof of the specific quantum effect being claimed. Now here is where the Majorana 2 announcement tries to close that gap, and where the story gets genuinely interesting from a science communication standpoint. Microsoft followed its February 2025 announcement with a separate preprint in July 2025 that finally included both X and Z measurements for the Majorana 1 chip, directly responding to the criticism from the spring meeting. Physicists Sergei Frolov and Henry Legg, two of the most vocal skeptics in this entire saga, reviewed that data and continued to find it unconvincing. Read that again slowly. Microsoft tried to answer its critics directly with the exact measurement its critics demanded, and the same critics still were not satisfied. That is not a minor detail. It tells you this disagreement is not simply about missing data. It is about a deeper, unresolved argument over what counts as real proof in a field still inventing its own rules as it goes. Like and subscribe, because this is exactly why the Majorana 2 paper's decision to publish only Z measurements again after all of that history raised eyebrows the moment physicists noticed it. Microsoft had already faced this exact criticism once before, already attempted to address it once before, and chose to release a brand new flagship chip without including the measurement type that triggered the controversy in the first place. Microsoft's own paper acknowledges the gap directly, framing the missing X measurements as future work rather than a settled question. Whether that is a sign of scientific caution or a sign of a company managing its messaging around an unresolved weakness depends entirely on who inside this debate you choose to believe. Now understand the role artificial intelligence is playing underneath all of this, because it is more central to the story than most coverage admitted. Microsoft Discovery, the agentic AI research platform credited with accelerating the Majorana 2 breakthrough, is designed to run autonomous AI agents that propose new material combinations, simulate their properties, and flag promising candidates for human researchers to test physically in the lab. According to Microsoft, Discovery helped identify the specific lead-based superconductor stack used in Majorana 2 far faster than traditional trial and error materials science would have allowed. The company chose to make Discovery generally available to the public at the same Build conference where Majorana 2 was unveiled, packaging both announcements as proof that AI-accelerated science is no longer theoretical, that framing matters beyond quantum computing specifically. Like and subscribe, because Microsoft is making a much bigger argument here than just our chip got better. It is arguing that artificial intelligence can compress decades of physical science research into a fraction of the time, and Majorana 2 is being positioned as Exhibit 1. In that argument, if true, the implications stretch into drug discovery, materials engineering, and climate science, anywhere humans have historically needed years of slow experimentation to find the right combination of variables. If the underlying quantum claim turns out to be overstated, though, the AI acceleration narrative built on top of it becomes a much harder sell to investors and scientists watching closely. Now let that sink in, because the financial stakes sitting underneath this entire debate are not abstract numbers in an earnings report. Microsoft's market valuation sits in the hundreds of billions of dollars, with quantum computing increasingly positioned as a core pillar of its long-term cloud and enterprise strategy alongside artificial intelligence. Every time the company announces a quantum milestone, it reinforces a narrative to enterprise customers, government partners, and institutional investors that Microsoft is years ahead of the competition in a technology many believe will eventually reshape national security, pharmaceutical research, and global finance. That narrative has real commercial value today, regardless of whether the underlying physics is fully settled tomorrow. Read that again slowly, because that commercial value creates a structural tension that never fully goes away. A public company has every incentive to announce progress early and often, because investor confidence responds to headlines in real time, while peer review, replication, and scientific consensus move on a timescale measured in years, not quarters. Microsoft is not unique in facing that tension. Every major technology company racing toward an unproven frontier, whether in artificial intelligence, biotechnology, or quantum computing, faces the same pressure to announce before the science is airtight. What makes Microsoft's quantum story unusually visible is simply how openly contested the underlying physics has become, with named physicists publicly disagreeing with named Microsoft researchers in real time, across multiple publications, for almost a decade. Like and subscribe, because here is a detail that puts the entire 2029 target into sharper focus. Even optimistic insiders inside the broader quantum computing field generally agree that going from a handful of working qubits to a million qubit, fault-tolerant machine is not a single engineering project. It is dozens of separate engineering projects stacked on top of each other, covering manufacturing yield, cryogenic cooling at scale, control electronics, software stacks, and error correction architectures, each of which has to work simultaneously for the final machine to function. Microsoft's 12-qubit Majorana 2 chip is, by its own description, a step toward solving the materials science piece of that puzzle. It does not address most of the other engineering mountains still standing between today's lab and a 2029 commercial product. Now here is a detail governments are not waiting around to resolve before acting, regardless of whether Microsoft's specific 2029 target proves accurate. National security agencies in the United States, the European Union, and across Asia have already begun mandating migration toward post-quantum cryptography standards, the new mathematical encryption methods designed to resist attack even from a future, fully realized quantum computer. That urgency exists precisely because nobody can say with certainty which company or which country will be the first to cross the finish line or exactly when. Like and subscribe, because this is the quiet, unglamorous side of the quantum race that rarely makes headlines, even though it may matter more than any. Single chip announcement, encrypted data stolen today, even if it cannot be cracked today, can simply be stored and decrypted later once a sufficiently powerful quantum computer exists. Intelligence agencies call this a harvest now, decrypt later strategy, and it means the clock on protecting today's secrets may already be running, regardless of how the Majorana 2 debate ultimately resolves. Read that again slowly, because that single factory frames the entire Microsoft story. It does not matter from a pure national security planning standpoint whether you personally believe Microsoft's physicists or Microsoft's critics. What matters is that a credible, well-funded, technically serious organization is now publicly targeting 2029 for a capability that would make current encryption obsolete. Even a modest probability that the timeline holds is enough to justify billions of dollars in defensive cryptography spending worldwide. Microsoft's announcement, contested or not, has already changed the calculus for governments and corporations that have nothing to do with quantum physics directly, simply because the downside risk of being wrong is too large to ignore. Now here is the closing twist that brings this entire story back to where it started. Microsoft told the world it had cut its quantum timeline in half. What it did not say in the headline of the announcement was that the chip behind that claim has not yet passed the test required to prove it is a real qubit at all. The press release spoke with total confidence. The physics, examined sentence by the people qualified to judge it, spoke with considerably more doubt. Somewhere between those two voices sits the actual truth about how close or how far we really are from a working quantum computer. Like and subscribe, because the most honest way to close this story is the way good science actually works, slowly, with disagreement, and without a guaranteed ending. Nobody watching this video right now can tell you with certainty whether Microsoft will deliver a working quantum computer by 2029, whether the company will quietly push that date back again the way it has before, or whether Majorana Zero modes will eventually be confirmed beyond any reasonable doubt. What can be said clearly is this: a trillion-dollar company has staked 2 decades of research, a significant share of its long-term strategic identity, and now a very public 3-year acceleration claim on a particle that some of the most qualified physicists alive still are not convinced has been proven to exist inside its hardware. That is not a small bet. That is one of the boldest, riskiest, most consequential technology wagers happening anywhere on the planet right now, and almost nobody outside the physics community is watching it closely enough to understand what is actually at stake. Now let that be the thought you carry away from this. The president of a quantum computing race wants you to see the finish line. The physicists closest to the track are still arguing about whether the starting gun has even fired the next time a company tells you it has cut a timeline in half. Do not just ask how, ask what part of the proof they conveniently left out of the headline.